Welcome to oniro-with-zyga. Let me show you a couple of things that relate to updating real devices. So let's start with the Raspberry Pi. Okay, in this terminal, I'm logged into a Raspberry Pi 4, which is running a daily build of Oniro, and I will show you around, and then we will upgrade this device to a latest build that I have triggered a few hours ago in this pipeline. It's like a daily build pipeline. At the time I loaded this page, it was still in progress. If I refresh, it should just be completely built. And in here on the right, you can see that we have published the Raspberry Pi update bundle and a bundle for a different board we'll look at later. So just look at this briefly. This is a pipeline that is fairly simple. It just takes the artifact from a previous stage. So looking at this, let's switch on one more thing and let me make sure it's visible in the shot. Okay. So this is showing the same set of jobs with those job dependencies highlighted. So this job, publish Raspberry Pi, depends on the bundle job for the Raspberry Pi, which further depends on a more comprehensive build job for the Raspberry Pi. So this specific one, the bundle, builds an artifact which is sufficient for the update process. So it's here, it's in images, Raspberry Pi, and there are going to be bundle files here, it's 72 megs. So going back, the publishing job, sorry, let me grab focus. Okay, the publishing job just takes this artifact and uploads it to Hogbit. And this is exactly what happens. There's a lot of verification for correct usage of this pipeline job. We create a software module in Hogbit. We create a distribution set in Hogbit, and we upload the artifact to this distribution set. Sorry, to this software module, and it's already been present in the distribution set. And we end up with this. So we have uploaded a build with this timestamp. I'm going to take this timestamp and copy it. And yeah, there's some information about the file that got uploaded. And here I'm conveniently logged in to our server. It's just our local Hogbit installation. And we can look through the distribution set and just use the same timestamp. So let me make this larger. So this is, as you can see, a build for the Raspberry Pi 4. Has the same version-based timestamp, was built on the 19th of May. So in a moment, we'll use this to update. But before we do, let's go back to the terminal and have a look around. So Oniro uses an A-B update model. So we have a full system image in slot A. When we update, we write a complete new full system image to slot B, and then back to A, and back to B. And we'll keep upgrading this way for as long as we like. And in case something fails, we always have a complete working system to boot from. So let's look around. I'll start with Rauk status. So Rauk is the layer which manages this A-B split. And as you can see, we have booted from slot B. Slot B is this partition on this specific device. And we can look at how this is expressed in the boot system. On Oniro images, the boot directory is part of the read-only image, so you will not find the real boot system here. It's just the kernel in this case. The actual boot files are located here. Run, mount, boot. And this is the actual fat boot partition. So if you're familiar with how Raspberry Pis boot, this will seem very familiar. There's a lot of files that are related to the bootloader. There's the start elf, there's the fixup files, there's bootcode bin, there's some device trees, there's the kernel, which is the actual kernel this device is using at this time. And there's also slot directories, and this is a custom thing we have created in Oniro. Let's look at the config file, which governs the whole boot process. So as you can see, it's a fairly short file, and the one highlight I have is obviously this OS prefix variable. So effectively, this tells the Raspberry Pi bootloader to load everything related to the boot process, so the kernel, the device trees, all the other configuration files from this directory. This lets us have a similar A-B split for the boot partition without having two separate partitions. So let's quickly go to slot B. And again, you can see a lot of the same files. We have a command line file, We have a config file, which is in this case not used, but it's the one that was used as a template for the actual ones we have booted from. We have the same start elf files, we have fixup files, and we have a kernel image. We also have the overlays directory, so any kind of overlays you have in your kernel will be loaded from here as well. This is interesting because it technically allows you to have an update which changes in an atomic step the kernel or the kernel modules or the device tree and even the bootloader itself. And in case this is failing in any way, there's a guarantee that it will go back to the previous slot. The way this works, I'll explain in a moment. Let's start the update because this will take a while. So going back to Hogbit and taking this timestamp in case I have not got it in my clipboard, let's find the right distribution. This is actually really crowded, and I plan to use the type system in Hogbit a little bit better so that when we select the device, only software compatible with that device will be available. So this will be less tedious to work with. And let's trigger the update manually. So just drag this to this device and confirm that we're gonna upgrade my Raspberry Pi to this build. And let's just get started. Oh, it's incompatible. Oh, I was trying out the new build system types. And this is indeed not compatible. Let's cheat. Let's change this so that it is compatible. It's type Raspberry Pi. I will just remove the type. So yeah, I was experimenting with this and now it's gonna work correctly. Okay, assignment is in progress. So yeah, I already had this idea and I was exploring it, and the builds that come out of the build system are still using the old model where there was effectively no types. And the Raspberry Pi device I was exploring this process with already has been configured to use the types, but we can still change it here. So this is in progress. Let's have a look at this UI. So I'm going to make sure that you can see this in the frame. On the right-hand side, you can see the action history for this device. And I think there's a way to make this bigger. Hold on. Yes, there's this arrow here. So now we can look at the action history of this single device, so all the things that Hogbit has asked this device to do. And as you can see, the upgrade is now action 15. And here we have interesting things. There's some status messages that show up. So first of all, I'll just make sure this is visible. Okay, it is. So the first one was target retrieved. So it's communicating with Hogbit. And in a moment, well, this can still take a while, but so let's be patient. It will discover that there is an update because this is a periodic check that the device is performing. Start the download process. You can actually look at how this looks like in one of the previous updates I did on this device because, this takes still a lot of time. Let me rearrange the window so it's visible in frame. Okay. Unfortunately, Hogbit user interface is not really friendly with like a small window when you're trying to fit multiple things in the camera. But you can see that there's a pattern of behavior. At this point, the device has discovered the download is available for it. It's going to perform the download. It's performing checksums, installing it. There's a progress for installation. And this is all these messages you're seeing are actually relayed from Raug to Hogbit using an intermediate program which connects the two. So you can see it's checking the bundle, it's verifying cryptographical signatures for it. Verification is done. It's checking a manifest, which is a technical file inside the bundle. There's a lot of these steps, but you get the picture. It's copying the image to the selected new slot, and the installation is done. So it's now downloading the new bundle, and let's actually have a look at the device. So as you can see, some of the same messages show up in the log on the device. Let me just double check that they're visible. The actual messages here are just going to be really technical. It's going to keep saying checking for new software until it's finished downloading. But in a while, you will see that it indeed has finished downloading, and all these additional steps we've been looking at in past updates will come to pass and will happen here as well. So let's just be patient. Let's have a look and wait. Or actually, let's make it a little bit more interesting and go back here. Go back here. Go back here. And let's do this for the other board. So we have a SECO Intel B68 target. And we've also published a build for this target into Hogbit. Let me tweak the types because I was playing with the types as well. So let's get rid of the types for a second. Let's paste this number here. This is the version, and let's drag this image onto my board, which is literally sitting on my desk right next to me. So we're going to do 2 updates at the same time. All right, let's go back to the Raspberry Pi 4. Let's zoom on the action history. Let's zoom on this one. Oh, it's already installed. Let's go back and see the logs. Ooh, we've missed this. I keep missing all these interesting pieces. So we can scroll up a little bit and see what happened. All right. And I've been saying the same story a few times already, so it's going to sound a little bit boring, but it's effectively fetching the bundle into a temporary location, it's verifying its signatures, it's mounting it, it's determining where it's going to copy it to, it's copying it to the desired slot, and it's running some post-installation actions, and that's it. It's telling back to, reporting this back to Hogbit that everything went fine in this case, because these things just work, they come from the build system. And as you can see, the device has finished the update process and now it's rebooting. And this is going to be interesting. So we're connected through the serial adapter. We should be able to see some of the boot messages that come very early on. Oh no, we do not see those messages. I'm sorry. To actually see those messages, you have to enable boot level debugging. Oh no, hold on, there is something interesting. So as I mentioned, the update on the Raspberry Pi is atomic in the sense that the entire update is not material. It doesn't really happen until we commit the process at the end after rebooting. So unless you can correctly reboot into the new system and commit, any power cycling of the device brings back the old system. And this is achieved with the try-boot mechanism. And we actually see that one of the last messages that the system was doing was rebooting with this try-boot request. And if I had enabled boot level debugging, you would be able to see that it actually read the try.boot.txt file instead of the config.txt file. So let's scroll all the way down. I mean, this should be fairly boring because all of these builds are coming from the build system. They have additional testing done on them and they generally just work. So I'm not surprised it successfully updated. Let's look at Rauk. If you remember, before the update, we were booting from slot B. So we're expecting to have booted from slot A now. And this is indeed what's happening. So we have booted from slot A, which is slot called system.0, and it's the one that has been booted. It's dev mmc blkey mmc block 0 partition 2. And we can look at the build configuration, sorry, at the boot configuration again. And the try.boot.txt file no longer exists because as a part of this commit process, it has been renamed to the new config file. So our new config file says OS prefix is slot A. And slot A has a copy of all the relevant boot assets that come from the image that have been copied before the before the reboot process. So it doesn't have to be atomic. We can try to copy for as long as we like all these assets into the slot subdirectory on the boot partition. So that's Raspberry Pi. Let's go back and check our other board. So it's still in progress. Let's zoom in on the actions. I'll just double check that you can actually see this. Sorry. All right. So again, very similar story. The only difference here that the boot stack is entirely different. And I will apologize because the serial adapter for this board is just disconnected because I was rearranging my desk. So here it is. I don't really have it plugged in. On this board, the boot stack is different because we're obviously not using PyBoot. We're using Grub. So it's a EFI firmware booting Grub, and then Grub using a script determining which slot to boot from one of the AB slots that we have in an identical setup on the Raspberry Pi. One thing that is really important to highlight, which is different from the Raspberry Pi, is that on this type of bootloader, we have the kernel inside the slot image. So the kernel is never actually copied outside of that slot. It doesn't have to be copied to the ESP partition, so the EFI system partition. It stays within the slot. So again, we can upgrade the kernel, all the kernel modules, and everything else atomically. Let's have a look. I think it has retrieve the update action and should start the download. Okay, that's really good. And let's have a look at some past actions. So it's this type of action that has happened. This is the boot that had happened before, like the update. Sorry, not the boot. So I'm just comparing the messages to see how this looks like. But let's keep looking at this one. Okay, so it's downloading the image now. The image for this board is fairly large. I think it's definitely not 17 megs. I think there is a lot of firmware inside that image for all kinds of pluggable PCI cards and USB devices that you may have that not exist in the Raspberry Pi build. So this image is fairly big in comparison. But the update process should look almost the same. Let me try to get the serial adapter plugged in while we wait. Okay. Let's bring back the terminal. I'll attach the adapter to my Ubuntu system. Should be enough. Okay. And now in a new tab, I should be able to go to the next TTY USB device. And yeah, we're at the new board. So let's log in as root. Looking at the log, it has started, but we still have a second. So let's look at the boot partition again. Run mount boot. So it's a completely different setup. We have the EFI. This is an EFI system, ESPS, EFI system partition. So this is that FAT file system where you have the EFI directory, underneath you have the boot directory, and then for this CPU architecture, this is what you have. There's the bootx64.efi file, which is grub compiled for this architecture. We have a grub file and we have a grub.cfg file. So the grub.cfg file is fairly long, but it contains all the logic to select the right slot and to boot from the right slot. And the grub.env file, it's not really meant to be seen this way. There are better tools at looking at it, but it's good enough. You can see that really only has one variable, which is called sysota boot active is slot A. And RAUC status is indeed consistent because it is slot A. So let's keep this rolling. It's going to reboot itself in a moment. I think it's still actually downloading this firmware, so it may take a while. So let's keep exploring. Let's look around. So one thing that's worth highlighting is that right now there are 3 files in this directory. As you can see, there's the grub.env file, which is our state. We have grub.cfg, which is the config file, and we have bootx64.efi, which is the EFI application containing grub. As a part of the work this cycle, we are trying to merge the grub configuration file into the EFI application. So during the update process, we only have to update one file atomically, and this is a lot easier and a lot better to do than to have 2 files and make sure they are updated in sync. The grub.env file, on the other hand, is really interesting because it is something that we can remove, and there's some logic within the boot script to recreate it if it gets corrupted in any case, to know which slot to boot from, even if we have lost this information which has been otherwise provided declaratively. So I keep talking, but I think we still need to wait a little bit. Let me just check how long it took the last time. So it was 13:40 and 15. Okay, about 15 minutes. Let's keep looking. Journal CTL. So let's see. Right now, I think we can just sit back and enjoy. What else is interesting here? Here. Apart from merging the configuration file into the boot binary, we also have another task to upgrade the boot binary itself atomically. And there's a simple way to do that, and there's a much better way to do that. We're going to start with a simple way because it's simple. We're going to get 80% of the job done quickly. We're just going to replace it by writing a new file and renaming. the better way of doing this is to actually rely on the EFI interface to ask EFI to boot into the new bootloader once. So we're going to have a two-phase boot process. Or two-phased upgrade process, where we're going to upgrade everything outside of the boot kernel, outside of the bootloader, so the kernel, the modules, and all the applications that are contained in the image. And if that is successful, we can try to upgrade to the new bootloader if it has actually changed with another atomic reboot. So we can ask the boot system, the firmware, to try the new bootloader once. If that works, we can just do the upgrade process we've been doing before, so just renaming the file. But if that doesn't work, we cannot do that. We can still keep having the old file under the original file name, and that file will be selected by default by the firmware. And this way, we can actually prevent catastrophic upgrades of even the bootloader components. This is different from upgrading the firmware of the board, but it's a lot better and a lot safer than many traditional approaches, which just hope there is no power loss or hope that nothing will break during these moments. So let's keep waiting. Oh, it's maybe also interesting to explain why this upgrade is so slow. As I mentioned, the image itself is fairly sizable. If I need to be precise, it is about 0.5 GB. And this is a full image. At this moment, we do not have Delta support yet, so the device is really downloading all this information to perform the update. But the deltas, which are on the roadmap, this should be a lot smaller from a typical build like that, where we're effectively updating to a next daily image. With the exception of compiler changes or a brand new kernel, which results in a lot of different modules being built, we should see very, very small updates. My past experience, these updates would be on the range of several megabytes, and consistent with the actual changes to the image. So we need to be patient. This will just take a while. So what else we have here? Let's use this. Let's zoom out of this board and go back to the list of targets we have. So as you can see, I have 3 devices in my small installation. I have a Raspberry Pi 4 and a Raspberry Pi 3. And the Raspberry Pi 3 is actually going to be very useful very soon for testing upgrades using U-boot. So if you're familiar with the Raspberry Pi bootloader, the official Raspberry Pi OS uses its own proprietary bootloader stack. But many software distributions change that so that bootloader still exists because it's required, but instead of booting into the kernel directly, there is an indirection with U-boot. And this effectively lets you use U-boot and all of its features and all of its interesting capabilities on a board like a Raspberry Pi. And this is exactly what I want to do, to explore how our update stack, Raux, SOT, and Hogbud, can work with a board based on U-boot. And I'm going to do this while I wait for a different board, which I actually want to use U-boot on, which does not have another bootloader. So it's going to be very handy for this. And U-boot is very similar conceptually to how, from the point of view of the update process, of how grub updates work in a EFI world, so in the non-legacy grub world. There is a component that executes that has some imperative logic. So in case of grub, that's grub itself. In case of U-boot, that's U-boot script interpreter. There's a script which we can provide and actually fuse into the binary itself in both cases. For grub, the one we have been looking at before. In case of U-boot, an equivalent script written in a slightly different language, the one that U-boot understands, which is more shell-like. And there has to be a piece of state. So in case of EFI, in a perfect world, you could just use EFI variables and not have anything like grub in the picture. You can just boot a kernel directly. With grub, its state is the grub-env file, which it can write to. And in the case of U-boot, there's a very, very similar mechanism for writing state persistently to some kind of storage. It could be a piece of NVRAM on the board. It could be a file on an SD card, on the FAT file system. It could be a reserved place in Flash. There's a lot of different options for a board which has U-boot support. But from the point of view of the script, it's all the same. You just ask it to save the environment. So identically, we could use the same boot protocol we have in case of grub. And if you recall, it was with this variable. There's actually a few more variables so that we can have the proper rollback logic and things related to that, but in essence, it's just the one we have booted from, and then we know during the update process to boot from something else. And we can have the same set of semantics applied to all of these bootloaders, no matter how they work internally, for as long as we can put a piece of executable logic inside. And we can, because both of them support this feature. So let's have a look at this. It's still downloading. It will be a while. So let's try to guesstimate how long it will be. So this has started. Let me zoom into the action history. It has started, well, quite a long while ago. So I'm not sure what's going on. Maybe someone at my home is using a lot of bandwidth and everything is just slower. There's one simple way to look at this. In the case of, okay, you can see this in the frame, yes. In the case of this configuration, we're actually saving the bundle file to the TMP directory. And if my script writing skills are not failing me, we can actually look at this in real time. So yes, just my network is slow at the moment, but it's not dead. And if we recall correctly, that was about 400 something megabytes in total. So as soon as this is finished downloading, all the other steps are going to be much faster. Oh, and there's one more extra piece which may explain why this is actually so much more slower than I remember. I ran out of spare SSDs, so this board is actually booted from a very old hard drive. So just spinning rust. So an extra level of making this slower. But as we can see, it's almost at 400 mark. Double check what the actual size was. Okay, 460. So let's just be patient for a while. After we have U-boot, grub, and pyboot, I was really wondering what is the next step. Is there an interesting bootloader to support? Is there something that is missing, which is a major feature in this requirement set? And I think the next very interesting development for the entire stack will be to extend all this existing feature set and support secure boot-like technology, where there's a lot of additional complexity related to what is permissible to boot. So the firmware has some understanding of some kind of root of trust, and the boot material, the kernel or kernel with additional data, has signatures which somehow relate to that boot of trust. And if you think about this, it's conceptually fairly simple, but gets kind of muddy when you can think about upgrades, rollbacks, and changes to the root of trust, or the set of keys that are trusted to sign the boot material. So taking our stack to extend this to this more secure world will be really challenging and interesting. And I think it's also a very required step in the modern world where everyone wants safety, especially when you look at devices at scale that have no human operator looking after them all the time. So when we are done with secure boot, then I will really look at another piece of the puzzle, which is embedded devices without Linux. But let's check. All right, we are making progress, and boom, this was fast. So what happened here? Updating, it's downloaded. Let's check some is okay. Slot status, verification, checking bundle done. Okay, let's go back to this one. And here I am also connected over a serial connection, so we will be able to see something because grub by default will display some messages. So yes, it's installed correctly. So just some clarification, when it says here that it's installed correctly, it's the last stage that Hogbit intercepts and actually monitors. After that, there's a wait period for software to settle. And after that, the device will reboot. And when it does, we will be able to see the bootloader informing us that it's performing this one-off boot to the other slots, and all of the boot messages will follow. So I think it's set for 3 minutes. So the waiting period is set for 3 minutes by default. You can also change it, and over time we will reduce it as much as we can. Right now it's there because the pieces, there are three related pieces. There's Rauk, there's Rauk Hogbit Updater, and there's Hogbit in the cloud. And they have some limitations when they work together on who can reboot the system. And so this workaround with waiting for 3 minutes is just a way to avoid that. But there's no piece of the stack that actually requires it. It's just a limitation that we are currently aware of. So I'll just keep this in focus. I'll hide the browser for a second so that we can look at what is going on. Okay, this should be good in frame. What is going on when the device reboots eventually? Maybe another interesting piece of information. So in case of the Raspberry Pi, we actually had to reboot in a really special way so that the boot firmware will be notified. We want to try the other slot once and load the other configuration file. If you recall, instead of loading config.txt, it would load tryboot.txt from the boot partition. In the case of grub, there's no such need because we can write to the grub config file from user space, and grub can read that config file at runtime when it's booted before the kernel. So we could actually reboot right now. I'm just not going to do that to convince you that this is indeed working and there's no cheating involved in any of those elements. So let's just be a little bit more patient, and this will be over very soon. I think this will be my longest video by far. I can hear the hard drive is clicking, it's doing something. Oh. Is it dead? Curious. Well, let's wait and see. Oops. We have upgraded. So I wonder if there's something that I was not thinking about. Maybe like grab resetting the board serial port on startup. Let's do one more try. So I just want to reboot. Reboot. Yep. Yes, something weird is going on. As you can see, this character here is not what I was expecting. I was expecting the system to shut down and tell me what's going on. And in my past experiments, when I was doing this interactively while I was developing the feature, it was connected not to a serial port, because I didn't have one at the time. It was actually connected to a display. And I remember seeing all these messages on the display itself. So perhaps, yep, we're back. So perhaps there's something extra needed to configure the bootloader to use the serial port in this case. So anyway, we're back to slot B after being on slot B before because it's a stable boot situation. We have committed the transaction. Let's look at the boot partition. Well, not the boot partition, at the boot, well, the boot partition. Yes, sorry, not the partition table. Run mount boots. So we have EFI boots, and there is the grubenv. Yes, it's in the frame. You can see that. So grubenv should now tell us about the other slot being active. So sysota boot active is slot B. And it is indeed consistent with what we see here. So I think this should be it for this video. Thank you for watching, and please explore all of this stack in more detail. I'm also really curious to know if you have any questions. The pipelines that build the images, the pipelines that publish the images are all public. They're also documented. There's documentation straight in the Oniro repository, so I can quickly show you where to find that even before you build the documentation. So if you go to the repository itself and go to the docs CI directory, there's a hidden jobs directory because all of the CI jobs are hidden before you instantiate them. And there is a job to build a Rauk bundle, and it's documented. This is the actual documentation for it. It's not fairly long because it's a simple job. And there is a similar one for publishing. This one is a little bit more elaborate. There's more information here. The publishing tool, which we have been, maybe it was visible briefly during the pipeline run. So let's look at the last scheduled one. This is this one. Let's look at the publishing job, at any of these jobs. And as you can see, apart from having the file being retrieved between those build stages by GitLab itself, we run the HawkBitCTL tool, and this one is also obviously open source and available to anyone who wants to use it. And you can easily use this in a CI workflow or in a script where you're working locally. You can just feed these images that you've been building into a HawkBit instance that you have running on your laptop for the same at the same time. So it's like the upload and download process is really, really fast. So all of these pieces are open. Please tell us what you think. Please share feedback. Please share issues if you find any. And thank you for watching. See you next time. Bye-bye.